Okay, so I want to give you guys an idea of sequences in series. Okay, so I think you guys know a sequence from a really, really long time ago. And I'm basically going to do this by example. So here's a sequence that you know from a really long time ago. 1, 2, 3, 4, 5, 6. What's going to be next? Thank you all. And so on, right? Okay, so this is a sequence that's oh my god, what am I talking about?
Natural numbers.
Okay, so these are the natural numbers listed out in order, right? Okay, what I want you to think when you look at this thing, this is what's called an arithmetic sequence. Okay? And what I mean by that is that the transition from step to step is what? Like
the same.
Yeah, you're just adding 1 at every single stage. Cool? You guys all good with this? So an arithmetic sequence, you should think those transitions are always adding some number. Cool? Okay, can you give me another example of an arithmetic sequence with a different adding number?
2, 4, 6, 8.
Okay, excellent, perfect. The next one is 2, 4, 6, 8, and so forth, right? And what's your transition map?
Plus 2.
Plus 2, plus 2, plus 2. Okay, so an arithmetic sequence really only needs 2 things to define it, right? I need the transition map, right? What are you adding at every step? And also what?
Where are you starting?
Where are you starting? Perfect. You guys good with that? Okay, here's another one that's defined by that kind of similar. So 2, 4, 8, 16, 32. Is this arithmetic?
No.
You're doubling.
No, this is flat, not arithmetic because, because you're not adding something at every stage. If you were thinking about adding something at every stage, right, you'd be adding 2 at the first stage, and then the next stage you're adding 4. This guy means that this thing is not arithmetic. That's cool. Instead, my transition map is multiply by 2 at every stage. You guys cool with that? You guys remember a word for this from Algebra 2 maybe?
No.
No. Good. Multiplicative would be a really great word, but we're not going to use that. So we're going to use geometric. Did you know this one? Okay, so a geometric sequence is one where the transition maps are all multiplied by some number. Oh, they're all the same number at each transition, right? Okay. So can you guys give me another example of an a geometric sequence?
The number 49, 27, 2 squared, 4 squared, 2 squared, 3 squared, 4 squared.
Oh, okay, good. Nice. 2 squared, 3 squared, 4 squared, something like that. Okay, so this is a good example of a sequence where I can easily determine the next one that is not arithmetic or geometric. Why?
Because you're not multiplying by the same number each time.
Yeah, I'm not multiplying by the same number each time. You guys see that? This is a little bit like maybe if I throw 1 squared on the beginning, right? It's pretty easy for me to come up with the next one. There's a very recognizable pattern. To my knowledge, this thing does not have a specific name.
Nope.
Exometric.
It's a sequence.
Not anymore. I would call this the sequence of squares.
Sure.
Yeah, like things like this come up. Sometimes we name them when they come up a lot or when we want to talk about them because they're interesting. This one we don't happen to talk about a lot because it doesn't have a convenient form. You guys see that? So what I mean by that is some of these are going to have convenient properties, and this one probably doesn't have a nice convenient property. Cool. There's that one weird thing. Never mind. Okay. Can you give me an example of something that's actually geometric?
3, 9, 27.
Okay. Sure. 3, 9, 27, 81, coming dot, dot, dot. Okay, so let me give you an idea here. I'm going to give some notation. So notationally, in any sequence, I'm going to write the whole thing as A1, comma, A2, comma, A3, comma, and so forth. Right? And I'm going to call this thing just brackets and AN. And then I'm going to tell you where the ends start. So the ends start at 1 and go to infinity. You guys cool with this? So this thing, right, is a list. You guys remember that? I use those braces for lists. So I'm just going to list out the ANs starting at 1. So A1 is my first thing, and we're not going to stop. You guys cool with that? So can you give me, in this first example, a general formula for AN? N plus 1. Oh, that's the next one, right? Oh, yeah. I may have been confusing because this one's too easy. This is AN is N, right? You guys see that? The first thing is 1, second thing is 2, the third thing is 3.
Okay, so.
You guys all with me on that? Okay, how about this guy?
A sub 2.
AN is 2N. Nice. Perfect. You guys got that? These closed formulas do not always exist. For this guy, I think we can come up with one. What are the ANs for the square sequence?
N squared.
They're just N squared, right? Okay. How about for these guys, my geometric examples? What's the AN for the one that's 2, 4, 8?
Two times 2.
And
Well, 4
times 2.
If only there was a way to talk about multiplying N 2's together, right?
Yeah, but not 2 then.
Think
yeah, that's what it
2 to the N?
is. I was
Okay,
thinking
see that?
N.
Okay. How about my 3's?
Was that really it? Or would that follow the same sequence though? Because I know you can get all those numbers from 2 to the N, but you wouldn't follow the same pattern. You couldn't get like.
Yeah, each 1 unit increase, right, corresponds to another power of 2.
Yeah.
Which is really all I'm doing, is multiplying 2's together. So out of this guy with 3, 9, 27, 81, what do you got? AN is
And there's
3 to the N.
Yeah.
Cool. You guys good with this? You ready for general sequences? So let me give you a very nice, precise definition of a geometric and arithmetic sequence. Okay? So an arithmetic sequence, right, starts somewhere, maybe A1, right? And then what's the next thing after A1? A2, which is got from A1 by what? Adding.
N minus 1.
Oh, I'm not sure what the number I'm adding is, right? You guys see that? But to get from A1 to the next thing, I'm adding some number. I'm going to call it K just for K. That's cool. All right, how do I get to the next thing? It's an arithmetic sequence, keep in mind.
A sub 2 plus K.
Right, so this was plus k. This better be plus k2, right?
Isn't A1 plus 2k?
Yeah, so this one would be either, right? You might want to think a2 plus k, right? But I know what a2 is. a2 is a1 plus k. So if I add k to a1 again, I get a1 plus twice k. You guys see that? What's the next one going to be?
A1 plus 3k.
No, not yet.
A1 plus 3k.
Okay, so the next one's a1 plus 3k and kind of so forth, right? Oops, comma, so forth. So if I wanted a condensed version of this thing, right, I could write braces, braces, and I want to go from n is 1 to infinity, and these things are what?
A1 plus k.
I think they're a1 plus
K minus 1.
close.
NK.
Yeah,
N minus 1 times k.
Why is it n minus 1?
Yeah, why is it n minus 1? So I started at a1, right? So that first one's a1. And it's just a1, there's no k's there. So that's my n minus 1. Because when n is 1, this piece should be 0.
Yeah, so you just get A1.
And then after the next one, then I need to add a k. You guys cool with that? It's a little bit tricksy, but you might want to spend a second to convince yourself. So
Just plug it in.
a1 plus 0 k's is the first term. a1 plus 2 minus 1, 1k, right? My second one. And kind of so forth. That's all good with this? So this is a general arithmetic sequence. They all look like this. They look like some starting spot plus some number of k's. And at each stage they go up by k. Are we good with that? Okay. So now maybe I'll leave that over there. So what's a general geometric sequence going to look like?
A1,
So we're going to start with A1, right? And then our next term is going to be, so
Depends on
A2.
K.
good, so, cool. So I'm going to call them multiply map R for reasons that might become apparent later.
R for reasons.
Yeah, R for reasons. K for kicks, R for reasons. Okay, so if I multiply by R, what's my next term?
R
Okay. So I'm going to write that as A1 times R. What's your next one?
A1 2 No.
R squared.
A.
There you go. A1 R squared. Right? It should be A1 R times R. So you get A1 R squared. And the next one should be A1 R cubed. Good. And kind of so forth, right? So what's my general?
A1 times R to the n minus 1?
Oops. So A1 R to the
To the n minus 1?
n minus 1.
Yes, sir.
N is 1 to infinity.
So each sequence, like the structure of it is like a shadow of what's next?
Yeah, so in a lot of cases, there's some kind of a structure that you can use to tell the general form of everything. You guys see that? Like, so there's one structure that dictates each and every element. Okay, let me show you a sequence for which that isn't true. Okay, so this is important enough that we gave it a name. that we named it after a guy. So the Fibonacci sequence, you guys know what this thing is?
Nope. It's the thing the universe follows.
Yeah.
Yeah. Okay, so there's a number of good reasons that this thing appears. We're not actually sure what most of them are, but we believe that there are reasons because it comes up really, really often. So this thing starts off with a 1, and then another 1,
And then 2.
and then 2, and then
3.
3,
And
and
5.
5, and 8, and where the hell are you getting these?
You're adding
You
one
add-
previously.
Yeah, you add the previous 2, right? So the next one is going to be 13, and the next one is 21, and the next one is
34.
34, and kind of so forth.
55.
You guys see that? Okay, this one does not have a convenient closed form like this. The best you can do with this one is tell what n plus 2 is. So where did you get one of these terms? You added the previous 2. So what are the previous 2 to an plus 2?
And
an and
A plus 1.
an plus 1. You guys cool with this? So this is the best you can do on this one. And this is called a recursive definition or a recursive rule. Okay? So that's the best I can get for the Fibonacci sequence with one little caveat. What do I need to tell you to start with?
Starts at 1.
Yeah, A1 is 1 and A2 is 1.
Well, A1 could arguably be 0.
Sure.
because-
Yeah, you can start the sequence at 0 and 1 if you want. I think traditionally we just start it with 1s. So, you guys cool with this? Is this one arithmetic or geometric? Neither. Most sequences, right, if you pull a sequence out of a barrel, it's not going to be arithmetic or geometric. What's up, Bob?
Oh, I was going to give a little fun fact about the Fibonacci sequence. The higher up you go, like say you go to A sub 20 and you divide it by A sub 19, the higher up n is, the closer it is to the golden ratio.
Yeah, that's true. So, an plus 1 divided by an tends to the golden ratio, this thing we call phi. This has a number of meanings, one of which is that there's a good reason to believe that this is the most irrational number.
The most irrational.
My PhD research was on that. So, yeah, there's a very cool thing about this. This number is the one that you make like this. Yeah, so this is a Fibonacci, or this is what's called a continued fraction expansion. This is very cool. It's just a number, so graphing it's not actually interesting. You can figure out exactly what phi is, because phi is 1 over 1 plus phi, and you can solve this. You guys see that? Maybe you could multiply both sides by 1 plus phi, figure out that phi plus phi squared is 1. Subtract 1 to the other side and use the quadratic formula on this. So phi squared plus phi minus 1 is 0. You guys see what I did there to get that? I just noticed that if this thing keeps going forever, right? Then this part is another one of those. You guys cool with that? So you'll find out it's like